Okay, in this video we're going to look at an application of Laplace's method to derive what is called Stirling's formula. There's a formula for approximating n factorial for large values of n. So we're going to start off with the gamma function. So we know that the gamma of n plus 1, which is equal to n factorial, is the integral from 0 to infinity of t to the power n e to the minus t dt. So we're going to derive an asymptotic approximation of this function for large n. Of gamma of n plus 1 as n goes to infinity. So what we are going to do first is we are going to rewrite this so that it fits the functional format of what we derived in the method, the Laplace's method. So the term t to the power n, we're going to write it as an exponential, and then these two exponential terms we can combine. So this is going to be n ln t minus t, and in fact this we can write as n into ln t minus t over n. So this is going to be our I of n. So in the terminology of the Laplace's method, so our phi of t is ln t minus t over n, which means phi prime is going to be 1 over t minus 1 over n. This tells us that the stationary point is going to be n. So we have, so that's our stationary point is actually a moving stationary point, because as n becomes bigger and bigger, this term is also moving. So our stationary point, if you like, is not, well, let's just say it's a moving stationary point. Okay, so our stationary point is moving. So this is going to be a bit of a problem, but we can work around it. So to work around this situation, because you can see that here as n goes to infinity, our stationary point is actually going to move towards infinity. So we need to devise a way of working around this. So what we do is we introduce a scaled variable. Okay, this is a technique that we have seen before. So we're going to let u be equal to t over n, which means dt is going to be n du. Then our integral is going to become so we had integral from 0 to infinity e to the power n into ln t minus t over n dt. So what this thing is going to be, when t is 0, u is going to be 0, and t goes to infinity, u is also going to go to infinity. So integration limits remain exactly as before. E to the power n, then ln t is going to be ln un minus t over n is u, then n times du. Then we're going to factor out n here, so this is going to be e to the power n. It's going to be ln u plus ln n minus u du. And then this term here is not a function of u, so that means we can factor it out. So it's exactly what we're going to do. It's actually going to work out to n to the power of n. So ln u minus u. Alright, so we are now ready to rework our stationary point again. So this time phi of u is ln u minus u, so the derivative is going to be 1 over u minus 1, and the second order derivative is going to be minus 1 over u squared. So our stationary point this time is just going to be 1. So phi of u naught is going to be negative 1, and phi double prime of u naught is also going to be negative 1. So if we plug this into our formula for Laplace's method, which is going to have n to the power n plus 1, then this is going to be e to the minus n, being like phi at naught times the parameter, which is becoming big, which is n, and then the square root term is going to be 2 pi over negative n times negative 1. So this thing we can write as n to the power n plus 1 over e to the power n 2 pi over n, and then can further simplify this. N over e to the power n. If we absorb the n into the square root, then the square root is going to be 2n pi, and so that is going to be our Stirling's formula, which is your approximation for n factorial for large n. This formula actually does very well. If you can try it yourself, like 30 factorial, and then you punch in n is 30 here.